Hello, everybody. How are you guys? This is the topic that we're going to actually cover today. So as you guys are coming in, we're going to actually use this topic right here to go over the different concepts with osmotic pressure for General Chem 2 students. So as you guys are coming in, come on in. We're going to get started. All right. So go ahead and grab your water, your notes, so we can get started. Now, right here, this is the formula. You see this formula right here? We're going to use it. We're going to use it. So let me zoom in a little so y'all can see that. There we go. All right. Osmotic pressure is equal to molarity times the gas constant times the temperature, the absolute temperature. And the units associated with it are ATM, meaning that's your pressure unit right there. So if you get, let's say, millimeters of mercury, you need to convert that, or you would have to use the appropriate gas constant for it. Okay. All right. So let me go ahead and pull up some of these problems that we're going to actually show you today. And listen, when I go through these problems, if you all have any questions, please let me know. All right. Please let me know. Now, I'm going to actually solve this problem on my whiteboard so I can erase when I need to. Okay. So right here, it says, what is the osmotic pressure in ATM of a 0.884 molarity sucrose solution at 16 degrees Celsius? Now, they're asking you about this, right? You got to know this is the formula that you're going to use. Now, how do we solve this? I'm going to show you. I'm going to show you. Now, you do need your calculators, okay? You do need your calculators because your calculators are going to play a role in how these problems are solved and using the correct number of significant digits. Yep, significant digits, some sig figs. They're here, okay? They are here. So I am going to put this formula here, okay? And again, this formula is from the flashcards that you guys see. Let me zoom in a little bit so y'all can see that, okay? I want y'all to marinate on this question for a moment. Tell me, do we have everything we need in order to solve this problem? Do we have all the numbers that we need in this problem? Yay or nay? Now listen, as you guys go through these problems in chemistry, the whole point is to get you all to analyze this process. Look at what you've got, okay? Look at what you got and see if you have everything you need in order to solve the problem. So I'm trying to get y'all to see it. So for General Chemistry 2, your professors are going to assume that you already know how to do certain things, okay? They're going to assume that. Now, whether they're right in their assumption is up for debate, but they're going to assume that you should already know how to do it, okay? That based on what was given, they gave you the molarity. Matter of fact, let me revise this problem. Since you're looking for this, okay, let me go ahead and tell you all what you need in order to solve this problem. You do need the gas law constant. So I'm just going to push this out the way, okay? And I'm going to put here the gas constant is 0.0, and let me zoom out a little. My bad, y'all. 0.0821 liters dot ATM, and these units are very important to know. Moles dot Kelvin, okay? So you do need that. The temperature. They gave you in this problem 16 degrees Celsius, but you've got to convert that to Kelvin by adding 273 to it. All right. And if you want to use 273.15, then that's your business. Okay. If you want to do that, that's fine too. So my answer here is 289, okay, Kelvin. Now, what else do we need to know? Yep, the temperature needs to be in Kelvin. That's right. What else did they give you in this problem over here? So in case some of y'all missed it, 0.884 molarity. So they gave you the big M, not for menopause, but the big M for molarity. Okay? Some of y'all might be too young to know what menopause is. Okay? You're not going through that. Okay? But not the big M for menopause, but the big M for molarity. Now, look at your formula right here. You've got osmotic pressure equals M. We got that. R, we got that. T, we got that. So you're looking for this little, it looks like the pi, okay? Looks like the pi in math. So your formula, okay, is equal to, it looks like this right here. It's equal to M times R times T. So all you need to do, guys, is plug those numbers in and cancel out your like terms, okay? Plug those numbers in and cancel out your like terms. So let's go ahead and plug them in, and I'm going to bring up my calculator to see if we are on the right track. So I'm going to go ahead and start over here so I can have some space. My M is 0.884. Now, the units for molarity is moles per liter. So I'm going to use that for a reason, and you're going to see why, okay, in a second, all right? So I'm going to put right here moles per liter. So I just replaced my M with moles per liter. My R, 0.8221 liters dot ATM moles per Kelvin. And then my T for temperature, 289 Kelvin. Okay, so I was trying to write it all out, okay, so that you guys can see that, okay? Any questions so far? All right, because the only thing that we're going to do left is cancel out our units, okay? Cancel out our units. So, moles, slash away. Liters, slashed away. Kelvin, whoop. That gets slashed also. So what's left over is ATM. And if we go back to our problem, it says, what is the osmotic pressure in ATM of a 0.884 molarity sucrose solution at 16 degrees Celsius? So the only thing you had to do was find the R, convert the temperature. They gave you molarity, but you convert it to moles per liter, and voila. These are your three numbers. We've canceled out our units. So let's plug this into our calculator. Okay. So here's the calculator right here. We're going to plug these in. Okay. All right. So we've got 0.884 times 0.8221 times, whoops, y'all, that should be 0. Y'all didn't even catch this. My bad. Y'all did not catch this. That should be 0.0821. Nobody caught it. Listen, when your professors make mistakes, you better catch them and tell them. I don't have any shame in my game when I make a mistake, okay? So let me start that over. 0.884 times 0.0821 times 289. This equals to your pressure, 20.9745. Well, guess what? We only need 3 of those digits. So the answer is going to be rounded off to 21.0. And I know some of y'all are like, wait a minute. Yep. Because look, we need 3 of those significant digits right there. That 9 tells that 0 to go up to a 1. So the answer becomes 21.0 ATM. That is your answer right there. So I'm going to write that off over here. 21.0 ATM. Okay? And I was trying to zoom out as much as I could so that you guys can see the whole board right here. Okay? Any questions so far from anybody? All right. So this says the average osmotic pressure of seawater is about 30 degrees, or excuse me, about 30.0 atm at 25 degrees Celsius. Calculate the molar concentration of an aqueous solution of urea that is osmotic with seawater. Now, it's funny that they're talking about that, right? Because you may be familiar with isotonic and all that good stuff, okay? So when you read a problem like this is one thing I like about the cards that are pinned to the comments. Right here, they give you terms like this: semi-permeable, permeable, look, with my North Carolina accent, membrane. What does that mean? This is also something that you guys learn in biology. It's basically a barrier that allows solvents to pass but blocks the solute. Now, why am I giving y'all that? There are certain words that you need to understand in this particular chapter, okay? There are certain phrases that you need to learn in this particular part of the chapter. So if you don't know what a solute is, oh, thank you, Positive Vibes. If you don't know the difference between a solute versus a solvent, you're going to get these questions wrong. And that's so important to understand when it comes to these types of problems right here. You see where it says molar concentration? See, so if we break it down like this, it says, what is a solvent for a saltwater saline solution? I'm going to see if y'all can break this down before we even get into this problem, because this is going to segue us to this. What is a solvent in a saltwater solution? I'm going to see if y'all can tell me. Is it salt, water, or salt water? What is the solvent in a saltwater solution? Okay. Kayla said water. Okay. Safa said salt water. Okay. I'm going to flip it over. Water. Water, water, water. And here's why. Very good, Zaria. Here's why. The solvent is what's being used to dissolve the solute. So what is the solute for a saltwater solution? Salt. So and basically we're saying that these two go together. Water and salt. Water is the solvent. Salt is the solute to give you the solution, the saline solution of salt water. So you see how this goes together? You see? Solute, yeah, what's the solute again? The solute is salt. So to give you all the visual, okay, let me give you the visual. It's like this in chemistry. The salt that you drop in is a solute, okay? The salt that you drop in is a solute. What was in here, you pour in your water, which is the solvent. Together, these two things together, you get a solution, which in this case is salt water. Okay? Solute is the salt, the solvent that's going to dissolve it. Hold on, y'all. The solvent, which is water, together, you're going to get your solution, salt water. Let's write down the numbers that we have just to make sure we are clear on what's given, okay? So if we go back to our formula from before, this is the formula. That little funny shaped pie right here equals M times R times T, okay? This is the formula right here. That little funny shaped pie. And I know that doesn't look like that, but let me redo it. Okay. What did they give us in this problem? They gave us several things, okay? But you got to know how to redo the formula in order to get what you're looking for, okay? You got to learn how to redo the formula to get what you're looking for. Here's the thing right here. This little thing right here, this is the osmotic pressure. This is what they gave us, 30.0 atm. They gave us that. They also gave us the temperature, which was 25 degrees, but we have to convert that to Kelvin. By adding 273 to that number, okay, you get 298 Kelvin. That's your temperature. Now, something else, your R that you need, 0.0821 liters dot atm per mole Kelvin. You've got 3 of these numbers, but what is missing? The big M. The big M. The M is missing, okay? The M is what's missing. And because the M is what's missing, when they ask you for what is the molar concentration, you're going to have to rearrange this formula to solve for your M. You're going to have to rearrange this formula to solve for your M. So I'm going to rearrange everything to solve for the M, okay? Now, because I don't have space right there, what I'm going to do, I'm going to move this here, and I'm going to actually write it down right there, okay? So that you guys can see that. So again, this was the formula, right? But what we are looking for is the M. I'm going to bring these two to the other side of town. So I'm going to basically divide both sides by RT, okay? So that we're left with M over here by itself. So the formula for M is going to be that little funny shaped pi over R times T. Okay? You see that? That's the formula right there. So, and look, we have all the numbers that we need in order to solve for the M. Okay? So I'm going to solve for that on this paper right here. Okay? So again, M equals 30.0 atm. That's on the very top. Divided by the gas constant, 821 liters dot atm moles per Kelvin times T, temperature, 298 Kelvin. Okay, see that? All right, so what are we going to do? We're going to cancel out our like terms, the units that we don't need. So let's cancel them out, okay? We're going to cancel them out. And that's, let me tell you, before you plug in any numbers on your calculator, go ahead and get rid of the units that you do not need. ATMs goes out the door. Kelvin goes out the door. You're left with, even though it says liters per mole, when you flip these units here, it's actually going to become moles per liter, okay? So now, when you flip this, it's going to give you moles per liter. So now we can go ahead and plug this into our calculator, okay? We can plug this into our calculator. So we've got 30.0 times, or not even times, excuse me, divided by 0.0821, and then divide that again by 298. Oops, and just like that, you only need 3 of those numbers. 1.226 becomes 1.23 moles per liter, which is the same thing as saying 1.23 molarity. Okay? Any questions from anybody so far? If you are taking General Chem 2, you guys are having to learn about your colligative properties, particularly with your non-electrolyte solutions and some electrolyte solutions. But in order to understand this, you have to know about Van't Hoff constant. You have to know what is a solute versus a solvent and all of that. Okay? Any questions before we move on to the next problem? The next example. Now, I want to tell you this too. When we get into these types of problems, and again, the reason why I love these cards, some of you guys probably can see the thing that's pinned. The reason why I love these little cards here in the packet that I got is because they also give you key formulas for each chapter. So you see how they break it down. They say, all right, concepts and definitions, and they give you the topic. So that way you're not looking through the whole box for certain things. You actually can just zoom in on what you need. So in this case right here, dealing with colligative properties, okay, let me zoom into the card so y'all can see it. How would you flip it if the temperature is not given? Well, if the temperature is not given, okay, you would have to find that. Now, so they're not going to give you this stuff without the temperature. Oh, you mean if you were trying to solve for the temperature, like solve for T in the formula? If that's what you're asking, I can do that. Yeah, let me flip the formula for that. I think that's what you're asking me. All right, so this is what you can do. To solve for your T. As a matter of fact, we're going to derive each formula, and this is what I would do. I would put all four, and the reason why I say four, well, actually, you need three formulas, because this R is going to be a constant that you look in the back of your book. You're going to have to look for M, T, or osmotic pressure. If you're looking for the temperature, you divide both sides by Mr. by MR, okay? So that you're left with T by itself. So T in this case will be equal to osmotic pressure divided by Mr. or MR, okay? So that is your formula for finding temperature. If you're finding molarity or molar concentration, this is that formula right there. And then if you're finding the osmotic pressure, which is that little funny shaped pie, it's the MRT as your formula. Okay, great. Got it. Okay, good. Okay. Now, these examples are all a part of even the concept of Raoult's law, okay? So you may have heard of that before, but what I want to do also is give you guys the formulas rather for each of these concepts. So for instance, if your teachers give you things like this, okay? They give you a formula sheet, okay? Guess what? These formula sheets that your professors give you can also be broken down into those cards, just like this. So for instance, you see where it says freezer point depression, okay? Whoops, right here. It says, what is the equation? Or what does the M represent? Well, we know it stands for molality, right? But again, if you didn't know that, these index cards helps you to find that or know that. Same thing right here. You have to know what each component in a formula represents. So same thing right here. If I give you the boiling point elevation equation, delta T equals K of B times M, if you don't know that that's the constant for a boiling point, you're going to be in trouble. Okay? So you've got to know what each of those things represent. And like, what does the M represent within the formula? Okay, what does the M represent? Molality. See? So they give you these things here. just to kind of have a quick referral, okay? A quick reference. So now, let's go back over here to our formula sheet. This osmotic pressure also has an I involved whenever they're talking about using the Van't Hoff factor in your problem, okay? So you would have to use your formula sheets that your professors give you in order to solve these problems. Now notice I did not include the I on this part right here, but it would be necessary if they told you to identify the Van't Hoff constant. And look, you wouldn't even have to use all this. You would just have to know what type of solution you're working with. If it's non-ionizing or ionizing, okay? If it dissociates or not. If it does, it breaks up into its ions. Like what I was saying earlier, magnesium chloride breaks up into the magnesium ion and 2 chlorine ions because of the subscript. So you have a Van't Hoff factor of 3. You would have to use this if they gave you a problem that required you to use it. Otherwise, you just use the formula here, okay, MRT. But some of your formulas will say IMRT. And that's if they're giving you the Van't Hoff factor as a part of the question, okay? Let me see if I can pull up a few problems that we can work on, you know, so that you all can feel confident about these problems. Another example. Okay, the first couple of examples that I gave you, the reason why we did not have to use that I was because they were non-electrolyte based, okay? They weren't electrolyte based. However, if I give you one where it breaks down, okay, in an electrolyte solution, then you would have to use this one. So let me say that again in a clear manner. If you are dealing with a non-electrolyte solution, use this formula here. If you are dealing with an electrolyte solution, you're going to use this one in purple right here, okay? Electrolytes, use the one in purple. Non-electrolyte, use the one right here in blue. So if we're dealing with, let's say, sodium chloride, magnesium chloride, solutions like that, you will have to use purple. But if I give you things that don't dissociate, use the one in blue. Okay, use the one in blue. So I do have some examples that we're going to go over. All right. Oh, and the reason why you use the one in blue is because it's going to be 1. The I is going to be 1. And so 1 times anything is going to be basically whatever the number is anyway. That is why. Okay. That is why. Now let's move here to those that will require us to use the one in purple with the Van't Hoff factor. Okay, let's use an example like that. We're going to do number 17 on my sheet right here, number 17. Okay, and I'm going to read it out to you. Number 17. It says a medical examiner analyzes a toxic solution with 0.15 molarity sodium chloride. Calculate the osmotic pressure at 310 Kelvin. Okay. We're going to use the formula in purple because sodium chloride is an electrolyte. Sodium chloride is an electrolyte because it breaks apart into sodium ions and chlorine ions. 1 + 1 gives us 2. So because we're going to use the purple formula, I am going to write it again here so that you guys can see that. Okay. All right. Again, I know that because it's sodium chloride, let me put this as a side note over here. The sodium ion is +1. The chloride ion is -1. And because I have one of each, I get 2 as my Van't Hoff. But let me break it down better for y'all, okay? We have the sodium ion, which is one of those. Chloride ion, which is one of those. Together, we have 2. So right here, I'm going to say 2 for my I. Now, I'm going to need more space, so I'm going to slide this over right here. All right, so you guys can see that. Okay. So this is going to give us 2 from what we calculated over here times, in this problem, they told us that the molarity was equal to 0.15, and I'm going to put moles per liter for molarity, times, now our R, that's that gas constant that we've talked about before, okay? So let me zoom out so y'all can see the whole board. 0.0821 liters times ATM per mole dot Kelvin times, and then the temperature they gave us in this problem was 310 Kelvin. Okay? All right. I'm going to let y'all look at that for a second. Okay? What we're going to do is cancel out our like terms. The units that don't make, that we don't need anymore, we're going to cancel those out. Okay? We're going to cancel those out. So we don't need liters, so we're going to cancel that out. See that? That goes away. We don't need moles. That cancels out too. Okay? So we didn't need moles. We didn't need liters. We no longer need Kelvin. So we're left with ATM because we're looking for the osmotic pressure in ATM. So all you have to do now, guys, is multiply 2 times 0.15 times 0.0821 times 310. So now let's plug that into our calculator and see what we get. All right. And so we'll do one more problem before we get out of here. Okay, one more problem. 2 times 0.15 times 0.0821 times 310. And we get 7 point. Now, we got our final answer should have 2 significant digits. So our answer is rounded to 7.6 ATM. That's our answer for that one. Okay? That is our answer. All right. So we're going to move to the next one. Number 18. Number 18. It says, a forensic biochemist finds a sample with 0.2 molarity calcium chloride. What is its osmotic pressure at 298 Kelvin? So what we can identify in this problem is this is an electrolyte. Calcium chloride is an electrolyte. So we have to break down calcium chloride into its ions. They also gave us the temperature. They gave us the molarity. And you just have to find the gas constant, which is 0.0821. All right. So let's do number 18 together. And again, I'll read the numbers out to you so you'll have the numbers again. Okay. Again, for an electrolyte, you're going to use this formula right here. If this was a non-electrolyte, MRT. Electrolyte, IMRT. Okay? Now, they told us this was calcium chloride. So, because it's calcium chloride, we're going to break this up into the calcium ion and the chloride ions. There are 2 of them for chlorine. That 2 right there represents the chlorine ion. 1 plus 2 gives us I equals to 3. Okay? The M, they told us, was 0.2. But I'm going to rewrite the molarity unit for moles per liter. They also gave us the temperature, 298 Kelvin. Okay? So now, and then again, the R, we know 0.0821 liters dot ATM per mole dot Kelvin. So these are all the numbers that you need in order to solve this problem, okay? Those are the numbers that you need to solve this problem. So let's go. This little funny shaped pie is equal to 3 times 0.2 moles per liter times 0.0821 liters dot ATM moles in Kelvin times temperature, 298 Kelvin. Okay, so let me back out a little so you all can see this better. Okay, multiply all of these numbers. We're going to multiply all 3 of those numbers. 3 times 0.2 times 0.0821 times 298. And we get 14.67, but we're going to round this to only needing one significant, we're going to actually use 2 significant digits right here, okay? So our answer, instead of saying 14.67, we only need 2 of those. So our answer here is 15 ATM. And I forgot to slash out our units, but by now you guys should know how to get rid of those, okay? Get rid of your moles, liters, Kelvin. What's left over is ATM. Just like that, we are finito. We are done. Guys, have a great rest of your evening or your day. And if you have any questions, just put them on my last video and I'll try to make sure that I get with you. Oh, thank you, Safa. I appreciate you. All right, and make sure that the next time you guys come back, bring a friend with you. Okay, bring a friend. All right, guys, have a beautiful rest of your day.